Welcome to Random Maths, and welcome to video 4 in the Finite Series playlist. In this video we will be discussing geometric series. Before I begin, I want to point out that I've changed the notation that I will use to define a finite sequence. So then if you rewatch the first video, you'll notice that the notation I used to define a finite sequence with n terms in was as follows. I would take the sequence a underscore r for r is equal to 1 to n to mean the list of all numbers, so a1 to mean the following list of numbers. Now, instead of that, I'm going to instead use the following. It's just a bit more compact and a bit nicer. It's the same list and the same definition, just a bit nicer. So going forward, I will be using the notation in the green box rather than the notation in the red box to define a finite sequence containing n terms. Okay, so let's carry on with the topic of this video, which is a geometric series. So the general definition of a geometric series is as follows. Take a sequence a underscore r. Sometimes I refer to these as AR because I can't bother to say underscore, but take a sequence a underscore r from r is equal to 1 to n defined by a underscore r is equal to k times x to the r minus 1 for k and x to be real numbers, and for r is equal to 1 to n, and obviously r is also a positive integer, so that's a member of the natural numbers. Okay, so take a sequence a underscore r from r is equal to 1 to n defined by a underscore r is equal to k times x to the r minus 1 for r is equal to 1, 2 to m. Then we say the sum from r is equal to 1 to n, so all the sums, so take all the terms in this finite sequence and add them together, of a underscore r, which is equal, because a underscore r is defined by this, so it's equal to that, is equal to the sum from r is equal to 1 to n of k times x to the r minus 1, which is equal to k times by the sum from r is equal to 1 to n of x to the r minus 1. Let me say the following series is a geometric series. So we take a sequence, which is, so the sequence is obviously going to be of the form, so this sequence is actually going to be equal to, it's going to be, well, let's have a look what the sequence is going to be equal to below. So we're kind of done with the definition for now, so I'm going to draw a line here. We're done with the definition. The sequence is going to look like, well, let's put r is equal to 1, then we've got a underscore r is equal to k times by x to the 1 minus 1, which is equal to k times x to the 0. Anything to the power of 0 is 1, k times 1, which is just equal to k. R is equal to 2, so then we've got so that's a1, sorry, not ar. a2 is equal to k times x to the r minus 1, so 2 minus 1, so 1, which is just k times x. Then we've got r is equal to 3, so we have a3 is equal to k times x squared, and so forth. So we'll go down to the nth term, so a underscore n, plug it into the a underscore r formula, is equal to k times x to the n minus 1. You can also think of these terms as well. Another way to define a underscore r as well, sometimes you'll see it defined as this. Rather than a underscore r is equal to k times x to the r minus 1, you may see instead a underscore r, so or a underscore r is equal to k times a underscore r minus 1. Okay, so x, get it right, so x multiplied by a times by r, a underscore r minus 1. And that's because if you look here, if you look at this one, well, except from that's obviously then that's good for r is equal to for r is equal to 1 to for r is equal to 2 to n. Sometimes it's referred to as that, and that's because, well, for a1 is just a1, so it's technically, bear with me a moment, sorry about this. So technically it will be k for r is equal to 1, and then a underscore x times a underscore r minus 1 for r is equal to 2 to n. And that's because from let's have a look, from well, let's keep in blue, from a2 onwards, let's have a look. We got a2 is equal to k times by x, right? Now k is equal to a0, which is equal to x times a0, and then obviously a3 is equal to so we got x times by kx. Kx is equal to a2, so that's x times a2, and obviously an, just because we can go an is equal to x times by k to the x to the n minus 2, which is equal to, because this here is then going to be equal to, because if we did it here we'd have an minus 1 is equal to k x to the n minus 2, so that therefore is equal to k times by a underscore n minus 1. So you can also, you may sometimes see the sequence defined like so. It's more intuitive to have it defined as such, because basically what we want to do is we want to define the sequence in terms of its first term. So we iterate until we hit a1, that backward plug it in, and this is the nice form that we were going to use. So this form. But hopefully you can see why it's also given in that form, and also why they're kind of equivalent. So you can say their statements are equivalent, really. But yeah, so this is we've got the sequence now. So the sequence up here, like I said, is just going to be k, and then it's going to be a1 times by x, not a1, well it will be a1 because k is a1, but sorry, let's keep it consistent, kx squared kx to the n minus 1, and we're going to take all these terms and add them all up, and that's going to be a geometric series. So that's a general definition of a geometric series. So if I put it in blue, the general definition is contained in this blue kind of box. Kind of run over the room. So the general definition is kind of defined in that blue box, and that's what a geometric series is. So let's look at a geometric series. Let's look at an example of a geometric series. But first, before we do that, we want to actually solve it in general, because currently what we've got at the moment is we're saying, so let's move on a bit, let's wiggly lines and move on. So this is just kind of explaining the sequence a bit. We'll corner that bit off. We're going on to a new topic now. So we can also kind of say, well, at the moment what we've got is a geometric series. So a geometric series is equal to k times by the sum from r is equal to 1 to n. I didn't really explain how I went from this step to this step. If you're not sure, check out my first video, and what you want to look for is when I talk about the scalar multiplication rule for finite series. I explain it and I prove it in the first video in this series, so please check it out, and that explains how I can go take the k out. Any term that doesn't depend on r you can take out if it's a multiple, put it to the front, and there we go. And also these I mentioned k and x as real numbers. All this basically means is you pick k and x. So we're showing examples. I'm just going to pick a random k and x, and then all the sequences will be generated from them by this term here, and then we'll have a sequence, then we just add them up, and then that's a geometric series. It's just basically what it means. A geometric series is you start with a value, and then each time you have a multiplier, and you multiply by the value each time. So you start with k, next is k times x, then multiply the last term again. So it's this iteration here essentially, this one in green. That's why I've kind of explained it a little bit. It's just multiply the last term by the common multiple, keep multiplying. So whatever the last term was, multiply it by the common multiple, then the next term multiply it by the common multiple, and that's kind of the pattern it goes in. So x is sometimes referred to as the common multiple. So I'll just mention that x can be sometimes referred to as the common multiple, such as d in an arithmetic series is sometimes called the common difference. This is also sometimes called the common multiple. So yeah, so that's kind of the gist of it. So yeah, so basically what we've got at the moment is we've got this x to the r minus 1, which is equal to k times by x to the 0 plus x to the 1 plus x squared all the way to x to the n minus 1, because when x is n, we've got x to the n minus 1, right? But that's obviously, well, let's just get rid of the x to the 0, because that's always going to be 1. So we've got 1 plus x squared. There's nothing wrong with this, and it is a solution, and we can solve series with it, but the form is not great. What I mean by that is, if we're looking at this sum, we want to simplify things, right? If we've got a sum, we want to simplify the sum, so we can, rather than adding n terms up, if we have a nice equation that we can plug figures in and get a solution, it could still depend on n, but there's no addition. There's the summation, the number of terms we've got to add up, or is going to hopefully reduce. That was the case when we looked at an arithmetic series. That was also the case when we looked at a telescoping series, and this is also the case when we look at a geometric series. This is why I did these 3 examples, because there are special cases where we do a little trick and we reduce the number of terms that we have to add up in the sum. So we may have to do a couple of operations at the end, but it's nowhere near n operations. So it's kind of like an algorithm to simplify the calculation to calculate the sum. So that's kind of what we're doing if you think about it like as a computation problem. So we're simplifying the number of terms. We don't want to add up all these if we can avoid it. Because imagine if you had 100 terms, 1 plus 2, you know, like 1 plus, depends what x is really. So if x is 4, 1 plus 4 squared plus 4 cubed plus 4 to the, 99, it's going to take a long time just adding it up. You have to compute it each time as well. It's still going to be a ridiculously high number, that solution, because 4 to the 100 is a massive number then. But you can still get the solution, even if you can't show it by writing it down. Well, you would be able to show it by writing it down, where you need a very long pad and it'd take a long time and it'd be useless, but you can actually find the solution still. Anyway, rambling, going off on the tangent, let's look at the little trick to simplify this sum here. So this sum here is obviously just going to be equal to, this sum here is just going to be equal to the sum from r is equal to 1 to n of x to the r minus 1. That's the sum. That's what this equals to, right? So both of that is equal to that. So let's simplify it. So remember before, so we look at this sum again. I'm going to write it again underneath. What we can do is we normally name an nth partial sum, because you're summing up n elements in a sequence. So that's why it's called the nth partial sum. What we can do is we just call that Sn, right? And we want to do something to get rid of a lot of terms, but also get another form for Sn. The trick is multiply it by x Sn. So this is what the proof is: multiply it by x Sn. So multiply the whole s underscore n. Sorry, not say again Sn. It's not Sn. It's s underscore Sn. But multiply the whole thing by x, and what you get is x times by 1 plus x squared, 1 plus x squared, all the way to x to the n minus 1, multiply it by x. What do you get? Well, you get x plus x squared plus x cubed, all the way to plus x to the n. So what we do is the trick. So this is the nice little trick that we do. The trick is, all we do is we do x Sn, s underscore n, minus Sn, and what does that equal? Well, let's have a look. We're going to take this. Oh wait, well, let's write it down again. So we've got x. So I'm going to write it down: x plus x squared plus x cubed plus x to the n minus 1, because these are what's common in this and this. So keep what's not common outside. So this is that whole thing given there. Then we're going to minus this whole thing. So we're going to minus, well, we're going to minus 1, because that's not in there. But then we're going to minus x plus x squared plus x to the n minus 1. We're going to take these two terms, cancel out, and we're just left with x to the n minus 1. This is also equal to, we can factor out the Sn times by x minus 1, which means we've got Sn is equal to x to the n minus 1 divided by x minus 1, and that's going to be equal to the sum from r is equal to 1 to n of r x to the r minus 1. So we can, I like to put it in this form, so I'm going to just write it again on the other side just because it's nicer to write it on the other side. So this is what we've shown. So basically when we go back to our original formula now, so therefore the sum, so therefore a geometric series can be solved by that. So therefore the sum from r is equal to 1 to n of k times by x to the r minus 1 is equal to k times by x to the n minus 1 divided by x minus 1. All I've done is I've substituted that sum to that, and that's a general formula for a geometric series. Let's show an example now. So we've got an example below. So we're going to just do two examples. The second example we're going to touch on infinite series. I mentioned it in the first video, but example 1 we're not. It's just going to be a general example. Let's take we're going to keep n general at first, then we're going to afterwards we're going to make it not general. But let's have a look. I'm also going to show that I'm going to do it naively and then solve it using the formula, and I'll show you that they're both equivalent essentially. But let's do an example. So we're going to make k is equal to, because I said you can pick these figures, there's nothing special about them, so you can pick them. So let's do k is equal to k is equal to 6. I'll put x is equal to 4, why not, and we keep in n general, so n is equal to m. So how do we sum this? So we've got what we want is we want to show that 6, so the sum of r is equal to 1 to n of 6 times by 4 to the r minus 1, which is equal to 6 times by, from r is equal to 1 to n to 4 to the r minus 1 is just going to be equal to 6 multiplied by 4 to the n minus 1 all over 4 minus 1, which is equal to 6 times by 4 to the n minus 1 divided by 3, which is just going to be equal to 2 times by 4 to the n minus 1, as so. So what I've done there is I've basically just solved it in terms of n. So now if I wanted to set a value for n, I can, and I can again get a generalized formula for it. So let's have a look. So let's make n equal to 10. I don't want to go too big because the numbers are uncontrollably large. In this instance, some instances they'll get really small, and then they'll converge and it'll be called an infinite series. That's going to be example 2, so stay tuned. But this is n equals 10. So if I'm going to do the sum from r is equal to 1 to n of 6 times, without moving it and stuff, let's just give it in its general form, that's going to be equal to 6 times, well, it's going to be, this is going to be naively, this is going to be 6 plus 6 times 4. I'm going to write it out in full. It's going to take me a while just to show you everything. I can do dot 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 as well, but for the first one I'm going to just write it out in full, because why not. Plus 6 to the 5, it's not too big, so 6 times 4 to the 5, not 6 times 5, plus 6 times 4 to the 6, plus 6 times 4 to the 7, plus 6 times 4 to the 8, plus 6 times 4 to the 9. That is going to be equal to 6 times by 1 plus 4 squared plus 4 cubed plus 4 to the 4 plus 4 to the 5 plus 4 to the 6 plus 4 to the 7, because you can factor out 6 because it's a common term, plus 4 to the 8 plus 4 to the 9. Now we can put that in a calculator and get the value. It's going to take a long time though, but we can do it. Let's have a look. So it's going to take me a while, bear with me a moment. So 6 times by 1 plus 4 squared plus 4 cubed plus 4 to the 4. So obviously it's taken a long time to type even this in a calculator. It's long. It's going to be longer for a computer as well. It's still going to be quick because computers are fast these days, but it's still going to be doing more operations. And if you've got some code or something and you're doing algorithms in a computer system, you don't want it to do more operations. So this is why having it in the other format is better. But bear with me a moment. So there you go. That equals 2,097,150. So bear with me. That's equal to 2,097,150. However, I could have just used a formula. I can just use a formula, which is much easier than doing all that in a calculator. So I've got R is equal to 1 to 10. Sorry, that's 10 as well. I'll rather put n there. N is 10 in this instance. R is equal to 1 to 10. 6 times by 4 to the R minus 1 is just going to be equal to 2 times by 4 to the 10 minus 1. So much easier just to do it like that. And it should give the same answer if I've done it right. If I've made some math error, it won't. So let's have a look. 2 times by 4 to the 10 minus 1. What does it equal? 2,097,150. Exactly the same. So that is good. So 2,097,150. They equate. So rather than doing that, we can just do that. So yeah, as you can see, it's much easier just to plug in, use the shorthand version. We've got two operations here. Well, we've got how many operations do we got here? We've got to do 2 multiplied by 4 to the n minus 2. So we've got to do a multiplication. That's one operation. Well, we've got to do 4 to the n first. Find out what that is. That's one operation. And then we've got to times it by 2 minus 2. So you know, it's not too difficult at all. So yeah, it's much easier to do it in this format when computing it. So now what that leads us to another question, right? Another example. That's what I was going next. Example 2. So example 2. This time I'm gonna keep it as 6. So I'm gonna keep we keep n general first again, but we'll keep k as 6. But I'm gonna change x to be equal to a half. So x is equal to a half, and I'm gonna keep n equal to n general first. So the geometric series I'm looking at this time. Oh, keyboard, I don't want that. Geometric series I'm going to look at this time is just going to be the sum. So I'm not going to write it out in full or whatever, but that's going to be the sum. We're just going to put the 6 outside now. I can't bother to keep doing this extra step. It's always going to be the case. It's the finite. It's the scalar multiplication of finite series. Look on the first video. R is equal to 1 to n of a half to the r minus 1. So what is this first and foremost? So let's have a look. So this is going to be equal to 6 multiplied by, so we're going to plug in the formula, what we had before. So let's have a look at the formula that we had before, because we've lost it. So it's down here. So if I I'm going to try something now. I'm trying to be use technology here. So I should be able to move that down. Yes. Ooh. Cool. And bear with me. So I'll just put it here. So that's the formula we've got. Have I moved it forward? Yep, so that's the formula I've got. So that's going to be equal to, well, we've already got the k, so that's a 6 here. That's the k. So we're going to just put a half to the n, so minus 1. So we've got a half to the n minus 1 all over a half minus 1. A half minus 1, so that's going to be minus a half. It's not going to be negative because this is going to be negative. That's kind of, it'll still be positive. Don't worry, because if you look at the top term, half to the end is going to be always less than 1. So that's always going to be, and then you're going to take 1. It's always going to be negative at the top. So then negative over negative is going to be positive. So we're not doing anything dodgy here. We're not going to get a negative answer, don't worry. 6 divided by a half is the same as 6 times 2. So we're going to have 12. So we're going to minus 12 times by half to the n minus 1. If you don't like that minus 12, we multiply in the bracket by minus and then the outside by 12. So we can also have 12 times by 1 minus a half to the n if you want. one of the terms has to be negative, not both. So cool. So that's the general kind of equation for that. So that's interesting. So we're going to pick some different values of n here for a moment. So we're going to look at the case where the sum from r is equal to 1 to 6 times by the sum from r is equal to 1 to 10. Let's try with 10 again. Yeah, so n equals 10. Of a half times by r minus 1. What we're going to get is so we've already got the general solution for it. So we're going to get 12 times by 1 minus a half to the 10, right? So let's get our trusted little calculator back up again so we can find out what that equals, because I'd have no idea. So 12 times by 1 minus a half to the n, but n here is 10, isn't it? Yep, 10. So minus a half to the 10, close brackets. So 12 times by 1 minus a half to the 10. What's that going to be equal? That's going to be equal 11.98882. So we'll just say 11.99. Why not? Interesting. So here we've got 11.99. Okay, let's make n a little smaller first. So what happens when n? I should have started when n is equal to 1, because that's almost what I'm trying to show now. Let's start with n equals 5. Let's go a bit smaller for the n. Then we've got 6 times by the sum from r is equal to 1 to 5 of a half to the r minus 1. What does that equal? Well, that's equal to 12 times by 1 minus a half to the 5th power. That's equal to, so we just change the value from here from 10 to 5. So I think I can do that by doing this. 11.625, okay. So it's still quite close to 12, but it seems to be getting closer to 12, doesn't it? Well, maybe not. Maybe if I put n equals 50 in here, it will come... Well, let's not go that high. Let's n equals 20, it'll go over 12 now. It should be at 12.5 or something, won't it? I'd imagine. Let's have a look. Is that the case? 6 times by the sum from r is equal to 1 to 5. 20, sorry, not 5. 20 times by a half to the r minus 1. What happens? Well, we've got 6. We've got 12, sorry, times by 1 minus a half to the 20. So this now, I mean, 11.625, 11.99 is going to be like 12.5, 12.2 or something, right? Surely. Let's have a look. No, we've got 11.999. We're even closer. So we got, if we do to, let's do 11.1234. Let's do 11.492856. 9998526. That's quite a big. That's very close to 12. But obviously it's going to go past 12 at some point, just slowing down, right? Let's put n equals 100 in. Now it's going to go past 12, right? Surely. We add in more and more terms, it should get higher and higher. It's going to go past 12, right? It's got to. You keep adding terms. It can't not go past 12, right? Right? Well, let's have a look. So 12 times by 1 minus a half to the 100. This is the last one I'm going to do, and it's definitely going to be over 12, I'm sure. Huh, 12? Exactly. It's not 12 exactly. What that means is the calculator cannot compute anymore. So let me try for load Windows calculator. It's not as good as that. It's hard to type on it, but we've got 12 times by 1 minus, and then bracket again, 0.5 bracket, and then we want to put it to the what was it, 200 was it? What was n? Was it 100, 200, 100 to the 100, close bracket. Yeah, no, something's gone wrong there. What's gone wrong? shouldn't be 0 point anything. 1 minus a half. 12 times by 1 minus 0.5 to the 100. 12 times by... Oh, I forgot a bracket. No? No? I don't know what's gone wrong there. I don't really know how to use Windows Calculator. So it's going to do the exponent first, 0.5 to the 100. And 1 minus that. I don't know what's gone wrong. What has gone wrong? Very weird. I'm not entirely sure what's gone wrong. But in any event, in fact, let's just expand the bracket out so we get it in basic terms. Yeah. Plus, minus. So 1 minus. So let's just do 0.5. 1 minus 0.5 to the 100. Oh, it mustn't have multiplied it by 12, I think. So 1 minus, yeah, bear with me, I know what happened. 1 minus 0.5 to the power of 100. Close brackets. Yeah. And then multiply this by 12. That's it. So it's not actually, well, it's a massive number. It's not actually 12. What it is 11 point, if you can kind of see the cursor. So let me just show you. It's actually, what it's going to be is it's going to be, we've got a red, that'll do, yeah. So however many terms here, then 1. But the calculator that I was using before doesn't go to this many terms. So it's just going to round it up to 12. So that's kind of exactly what it's done. Okay, bear with me a moment. So let me just close that. So it's not exactly 12, but it's 11.999999999. So they just round up to 12. Okay, the reason is, back to the lecture at hand now, the reason that's just come to 12 is because when we take the limit, so if we look at the original, so what we've got is we've got the 6 from r is equal to 1 to 100 times by a half. This is, we haven't discussed limits yet, and this is going to come up in calculus and analysis lectures. So we haven't gone over this yet, but I'll kind of give you the intuition. So 1 minus a half to the n. So ignore the 12 for a moment. Ignore multiplying by 12. If we take the limit as n tends to infinity, this just means what's happening as n gets bigger and bigger and bigger, of a half to the n. That's the only term that's got an n in it here. This term. What's going on with a half to the n? Well, this is equal to 1, because 1 to the n is just 1, over 2 to the n. Now what happens to a number when the numerator stays the same and the denominator gets bigger and bigger and bigger? So when n equals 1, we've got 1 divided by 2, which is just a half, which is 0.5. When n is equal to 2, we've got 1 divided by 2 squared, which is 4, so 1 over 4, which is 0.25. When n equals, let's just go to n equals 10, so 2 to the 10, I've got a calculator freehand here as well, rather than going to the other screen. 2 to the 10 is 1024, so that's 1 over 2 to the 10, which is 1024, and then 1 divided by 1024, that equals 0.00 9, no, one more naught, 9, 1, 2, 1, 2, 3, yep, 7, 5, 6, 2, 5, essentially it's just naught though, to 2, to 1 decimal, to 2, even to 3, even to 2 decimal places, it's still going to be naught. So basically, as n gets bigger and bigger and bigger, so when you got a really big number, like 2 to the 1000 or something, which is too big to even compute, it's going to be 1 over a massive number, so it's going to be 0.00000. Essentially what it means is as n gets bigger and bigger and bigger, and as n gets closer and closer to infinity, this gets closer and closer to 0. That's all this means. And how we're going to define infinite sums is as follows. So we haven't looked at it, and we're not going to look at it. This is a finite series, but an infinite sum. So what we can say now is the sum from r is equal to 1. Change this to n. Change this to infinity. of a half to the r minus 1 is equal to the limit. So when we're talking about infinite sums, we're talking about if we keep summing up terms and we get bigger and bigger and bigger and we go towards infinity, what does the sum get closer and closer to? It gets closer and closer to 12. It's never going to be 12 exactly, because we can't sum infinite numbers up. But it's going to be so close to 12 that we might as well call it 12. So we just use a sum for infinity, but we get around it in maths by just defining the sum, the infinite sum, to be a special case where it's a limit from n tends to infinity. So it's never equal, but it's practically equal. It's kind of like it is equal, but it's not. It's not equal because you can never get to infinity, but it's that close. I mean, come on, just call it 0, call it a day, right? It's close enough. Screw it. Pardon, I won't swear on these videos, but the F word, you know, come on, screw it. It's going to be basically it. So, and that's just going to be equal to the limit of n goes to infinity of the value, so of, what was it? We've got it up here somewhere, haven't we? We've moved it over. 12 times a half to the n minus 1. 12 times by 1 minus a half to the n, which is equal to, so that just goes to 0, which is just equal to 12. Which is equal to, well, 12 times by 1 minus 0, because this tends to 0 as n tends to infinity, so it's just equal to 12. So when we're summing an infinite number of terms up, we have to take the limit as n goes to infinity. But infinite sums aren't always defined, because sometimes it doesn't, if something doesn't converge, we can't say what it is when it has to converge. The limit has to converge. So when we had our first example, the number's going to get bigger and bigger and bigger and bigger and bigger, so we can't look at what it is when it's going to be infinity, and that's because in the first example we've got this here. So in this example we had 4 to the n here. When we take the limit of, as n goes to infinity, of 4, so infinite series aren't always defined. Finite series are always defined. You know, from 1 to n you can always add numbers up. From 1 to infinity you can't always add numbers, you can never do that anyway. But when this finite series, the function that it's equal to in terms of n, if that tends to a number as n tends to infinity, you can make it equal to that, but you can't if it doesn't. In this case, we're going to look at what 4 to the n tends to as n tends to infinity. Well, it doesn't tend to anything. It's equal to infinity, really. You can say it equals to infinity, and you can't say the sum equals infinity, because it does equal infinity. Do you know what I mean? So this is not defined. Only convergent infinite series are defined. But we're not going to, I've really glossed over this and not gone into too much depth. We're not going to go over it in this video series, it's finite series, but there is such thing as infinite sums, and in cases where the term converges, it's going to be an infinite. So basically, when modulus of x is less than 1, this is when it's going to tend to 0. This will tend to 0. So modulus of x is less than 1, we're going to have that k times by the sum from r is equal to 1 to infinity of x to the r minus 1. Essentially what it'll equal is k, this will be 0, so k times by minus 1, and it's going to be times by x minus 1, or again we can mitigate that, k times by 1 divided by 1 minus x. Multiply that bottom by a negative, top by a positive, so make it the same. So an infinite sum with a geometric series is that, but it has to converge, and it converges when the modulus of x is less than 1. When that's less than 1, that's going to tend to 0. Otherwise it's going to shoot off to infinity, and there's no way of defining an infinite sum then. So yeah, it's kind of glossed over. It's not into too much detail, but that's all I'm going to go over in this video. It's gone on long enough, this video now. I gave two examples, showed you what a geometric series is, and I'm going to actually show an application of a finite geometric series in relation to mortgage loan repayments. So that's going to be quite an interesting video, and it's going to be the next video and the final video in this finite series playlist. Thank you for watching this video, and if there's any comments, please leave your comments below. Any advice on how to improve these lectures will be taken as well. Any criticisms, literally anything you get stuck on, or anything you don't understand, any criticisms, any advice, anything you want, please put in the comments below. I'll try and respond, and I'll take on all advice for future videos. Thank you for watching, and I'll see you in the next video.